Hi everyone. In this video we're going to be learning how to determine the intermolecular forces found within actual chemical compounds and molecules. So here's a brief list of how to go about doing it. So if I was to give you a molecule, the first step you want to do is to draw its Lewis dot structure in order to determine its polarity. Now, if you determine that that molecule is nonpolar, automatically the strongest force of attraction is going to be London dispersion forces. It just depends on how those electrons are moving around and that temporary dipole forms. If it's polar, it could either be a dipole-dipole force of attraction is its strongest, or hydrogen bonding could be its strongest. In order for it to be hydrogen bonding, again, that hydrogen has to be connected to nitrogen, oxygen, or fluorine, and the force of attraction is between an unshared pair on one and the hydrogen of another. So we're going to look at 3 examples of this, and then you can work on the practice on page 3 of your packet of fun. The first one we're going to look at is CH4. I already have it drawn out because we've already gone through how to draw out Lewis dot structures, but you'll have to do that on your own in each of those examples. Now, if you notice, this one is the same on all sides, and you can determine very quickly that it's a nonpolar molecule. If it's a nonpolar molecule, the only forces of attraction that are going to be between CH4 molecules and other CH4 molecules are going to be London dispersion forces. And this is a very weak force of attraction. And that's actually why methane is present as a gas on Earth. Because there are these London dispersion forces, because the compound is nonpolar, it evaporates very easily, and it's very hard to get it in liquid form because these forces of attraction are very, very weak because they're London dispersion. The next one we're going to look at is water. Now in water, when we're determining the polarity, again, you want those unshared pairs on the same side so that you can see that the molecule is bent versus linear. And we do see that since there are those unshared pairs there, that this molecule is bent, and therefore this molecule is polar. Now we have 2 options when we have a polar molecule: dipole-dipole and or hydrogen bonding. So if something's hydrogen bonding, it's dipole-dipole and hydrogen bonding. But if it's not hydrogen bonding, then it's just a dipole-dipole force of attraction. Now for this one, we do see that we have a polar molecule, so it's definitely dipole-dipole. So the next thing we want to ask ourselves is hydrogen connected to nitrogen, oxygen, or fluorine? And it is. We see the hydrogen here that's bonded to the oxygen. So because of that, the strongest force of attraction is going to be hydrogen bonding here. Now, this is definitely a stronger intermolecular force than the CH4 that we just looked at, and that's why water exists as a liquid versus a gas, and it actually takes energy to break apart water molecules. Because the intermolecular force is a bit stronger, you need to give it energy in order to break apart those forces of attraction. The last one that we're going to look at is H2S. Here, it looks just like water. We have the hydrogen bonded to the sulfur. The sulfur has 2 unshared pairs on it, so therefore it is a polar molecule. I know that the arrow is going up toward the S because compared to hydrogen, sulfur is on the right-hand side of the table, so it's much more electronegative. So all those electrons want to go toward that S, so we end up getting a partially negative side and partial positive sides. So we quickly see here that we have a dipole that forms. Okay. Now we want to ask ourselves, well, is hydrogen bonded to nitrogen, oxygen, or fluorine? And the hydrogen's bonding to a sulfur, so it is not. So the strongest force of attraction here is a dipole attractive force, because this is a polar molecule and that hydrogen is not bonded to nitrogen, oxygen, or fluorine. So it's just dipole-dipole.